My dear students, welcome to the first class of this aerodynamics, which is intended for GATE 2021. So we will start with the aerofoil nomenclature. Consider the wing of this aeroplane, and you can see the cross-sectional shape obtained by the intersection of the wing with the perpendicular plane, that is the dotted line you can see, is called an aerofoil. And you can see a large illustration of that aerofoil over here, where you can see some basic terminologies are described. The major design feature of an aerofoil is shown in this diagram. You can see that is the mean camber line, which is denoted by this green dotted line, which is locus of points halfway between the upper and lower surface. Now you can see the most forward point of this aerofoil is known as the leading edge, and the most rearward point of this aerofoil is known as the trailing edge. And the straight line connecting this leading edge and the trailing edge of this aerofoil is known as the chord line. Basically, this trailing edge and the leading edge, the shortest distance, is known as chord, which is denoted by the C. The camber is the maximum distance between the mean camber line and the chord line. You can see over here, this is the camber. This is the mean camber line and this is the chord line, and distance between these two is the camber. So the camber, the shape of the mean camber line, and to the lesser extent the thickness distribution of the aerofoil essentially control the lift and the moment characteristics of this aerofoil. So we can see some more definition over the next slide. In this figure you can have some more definitions which are illustrated, which is with respect to an aerofoil which is inclined to the streamline of air. This is the streamline of air, that is the relative wind, which is coming actually opposite direction to that aerofoil. So the free stream velocity, that is denoted by the V infinite, is the velocity of the air far upstream of the aerofoil. The direction of this V infinite is defined as the relative wind. The angle between this relative wind and the chord line of the aerofoil is known as the angle of attack, which is denoted by alpha. You can see over here. So all the aerodynamic forces acted in an aerofoil is described over here. You can see. So the resultant force is R, and this is the lift force, which is actually countering the weight of this aerofoil, and this is the drag force, which is actually exactly opposite side. Okay, that is the backward side force. And you can see in turn the aerodynamic force R can be resolved into two forces, that is L and this D. Okay, so you can see these two forces are actually the lift and drag force, and the drag is always defined as the component of the aerodynamic force parallel to the relative wind. This is the parallel to the relative wind. And the lift is always defined as the component of the aerodynamic force which is perpendicular to the relative wind. You can see the perpendicular force. In addition to the lift and drag, the surface pressure and the shear stress distribution create a moment. You can see the moment. As you can see, all the force calculation is done at about, that is the 1/4 of this chord length, that is C/4. So you can have the moment about this C/4 length. So that moment tends to rotate this wing. with this lift and drag force and the reaction force, we are having one normal force and another is axial force. So we can represent this lift and drag by some equation with respect to this normal and this axial force. We will see that thing. So returning to this figure, you can see we recall the resultant aerodynamic force, that is R, and that can be resolved in two actually component. One is parallel and another is perpendicular component. So that is, the perpendicular component is that lift and the parallel component is the drag. And an alternative to this system is to resolve this R into component perpendicular and parallel to the chord line. So that can be seen in this figure, where we can have one normal force and another axial force denoted by N and A, and therefore we can represent this thing, these components, that is the normal and this axial force, in lift and drag equation. That can be seen over here. We can write down this lift very easily: N cos alpha minus A sin alpha, and drag is equal to N sin alpha plus A cos alpha. That is, actually we can get it by resolving these forces. So for aerofoils and wings, the use of N and this A to describe the aerodynamic force dates back as early as work of Otto Lilienthal in 1889, as published in his book Bird Flight as the Basis of Aviation. Indeed, the famous Lilienthal table, which were used by the Wright brothers to design their early gliders, which are used to actually design their primitive aeroplanes, can be dealing with these axial and these normal forces. The Wright prefer to think in terms of lift and drag, and they convert this Lilienthal result actually to their lift and drag table. Okay, so by this way we can relate this lift and drag to this normal and this axial force. So these two things, this lift is equal to N cos alpha minus A sin alpha, and drag is equal to N sin alpha plus A cos alpha, is very much important, because these are the conversion where we can get the Lilienthal theory is being merged with the Wright brothers theory. Now let us examine the variation of lift coefficient, that is CL, and the angle of attack, that is alpha. So we represent the vertical axis, that is y-axis, in respect to CL, and the horizontal axis, that is the x-axis, with respect to this angle of attack or alpha. So let us examine this relation of this CL and alpha more closely. The variation is actually represented in this curve, and the experimental data indicates that CL varies linearly with alpha over a range of angle of attack. Thin aerofoil theory, you can see, which is subjected to more advanced books on aerodynamics, also predicts the same type of linear variation, and the slope of this linear portion of the lift can be designated by A0, where that is dCl by d alpha, that is the lift slope. And you just note that when this alpha is actually 0, that is still a positive value of that is CL is still positive there, you can see over here, and this is due to the positive camber of the aerofoil, and all aerofoils with such camber have to be pitched to some negative angle of attack before the zero lift is obtained. And the value of this alpha when the lift is 0 is defined as the zero lift angle of attack. You can see over here, that is the alpha L0, and it is actually, you can very clearly see over here. And this effect is further demonstrated where we can see the lift curve of the camber aerofoil is compared with the symmetric aerofoil in the next picture. Here you can also see, after a certain angle of attack, the stall is actually happening due to the separation of flow, and that is also beyond reaching the maximum angle of attack. and that is to be a very cautious point for the pilot to maintain that angle, because beyond which you cannot have a very good lift, rather your plane is going to stall suddenly. You can see both the pictures where the lift curve for the cambered aerofoil is compared with the lift curve of a symmetric aerofoil. And you can note that the lift curve for the symmetric aerofoil goes to the origin. You can see over here, and where you can just recall the previous diagram where I can see in other extreme for the larger value of this alpha, that is the angle of attack, the linearity of the lift curve actually breaks. That means the stall occurs due to the separation. So as the alpha is increased beyond a certain limit, that means at that maximum value of that is the CL max is reached, that is the maximum lift coefficient is reached, and that time it suddenly drops, that means the stall occurs. So further increment of this alpha actually add nothing to it. So in this situation where the lift is rapidly decreasing at high alpha, that is high angle of attack, is known as the stall. So the phenomena of aerofoil stall is critically important in aeroplane design. So it is caused by the flow separation phenomena of the upper surface flow and the lower surface flow of the aerofoil. So in this diagram you can see in symmetric case the lift curve is actually goes to the origin, but in case of cambered aerofoil, due to the camberedness, you can have some amount of lift coefficient, though the angle of attack is 0. You can see over here. So now we will be discussing some important topics that has to be given some preference in gate point of view. So first thing in aerodynamics that students should concentrate, that is the continuity equation. So we know the general form of this continuity equation is delta rho by delta t plus gradient of rho velocity vector is equal to 0. So this is the continuity equation. This is the general form, and from this equation we can derive some form for steady flow also. So when I say for steady flow, this equation becomes, for steady flow, we know delta of delta t is equal to 0. That means with respect to time there will be no change. So the gradient of the density and the velocity vector will be 0 in this case for steady flow. Now if we consider another case, that means for steady and incompressible case, incompressible flow. So there the gradient of the velocity vector will be 0. Therefore, as we know, the density is actually constant over here. So this is for the steady and incompressible flow. So let us move to the next topic, that is drag on a body. Drag on a body. Let us draw one schematic diagram where this represents the relative winds, and if we take some control volume over here, and if this is the body in the form of an aerofoil, and this is something we know as the velocity gradient, is the height h. So if this is the y direction and this is the x direction as the conventional Cartesian coordinate, and if this is the control volume and the inlet density is ρ1 and inlet velocity is u1 and inlet, therefore the circulation, that is the tau, also represented by this double integral or surface integral of curl of velocity vector to ds. And another thing we should take into consideration, that if the flow is irrotational, if the flow is irrotational, then obviously this tau circulation is equal to 0. You should actually remember this, and this is very important funda to be remembered. Now when we just move to the next segment, we can find two important topic. One is psi function or the stream function, as we all know it, psi function or stream function, and which can be actually expressed by some equation like u is equal to del psi by del y, and v is equal to minus of del psi by del x. So this is actually about the Cartesian coordinate. Now if the same thing we represent in polar coordinate, we will get the radial component of this velocity, that is vr, which is nothing but 1 by r del psi by del theta, and obviously the next part, that is the tangential component, is v theta is equal to minus of del psi by del r. So this part of this stream function, which is denoted by psi, is very much important, and we need those equations actually further to describe other flows like doublet, sink, source, all this type of flow which I will describing. Actually for those expression we will be using this kind of equations. Now moving to the next segment, that is the velocity potential, that is denoted by phi, that is velocity potential, and actually it is nothing but can be represented with this equation, that is v vector is equal to the gradient of phi. So this is very, very important, because this relation you can use in many problems when they ask in GATE. So we can use this kind of expression with the help of this kind of expression, maybe not purely numerical question, but some fundamental question where they judge your understanding of these aerodynamic concepts. So there you can use this kind of facts. Now I will discuss some important facts, like some important cases when any irrotational and incompressible flow has a velocity potential and the stream function for 2D flow that both satisfy Laplace equation. That means it's equal to 0, and obviously psi is equal to 0. So this is VVI, very very important in gate point of view, because you can use this kind of fact to answer some questions, some logical questions in gate. So again I am repeating the condition: any irrotational incompressible flow has a velocity potential and stream function for 2D flow, obviously, actually, that both satisfies the Laplace condition. So this Laplace equation is about this thing, you all know about this thing. Okay, so after this we'll jump to the next topic, that is the uniform flow. A uniform flow is nothing but where we can get a uniformity of the flow characteristics throughout the flow. So in layman term, that is the uniform flow. And for uniform flow, some condition should be achieved. That is, the gradient of velocity vector will be 0 and the curl of velocity vector will be 0. Both the conditions should be satisfied. And with these conditions, if the tau, that is the circulation, the tau is 0, if the tau is 0, with this condition, additionally if this tau is 0, then we have to understand, or we should consider, the circulation around any closed curve in a uniform flow is actually satisfies these conditions. So circulation around any closed curve in a uniform flow satisfies these conditions, this condition and this condition. Or else I can say, if this condition satisfies, that means we can establish a circulation around any closed curve in a uniform manner. Moving to the next topic, we can have with this uniform flow some velocity potential, that is phi is equal to V infinite x, which can be expressed as V infinite r cos theta. Similarly, we can have for psi function also. We can have the same thing for the psi function also. That is the stream function. So that is V infinite y, or we can express it as V infinite r sin theta. As actually y is the perpendicular part, so we are actually taking that r sin theta for that y, and for x, as it is the horizontal part, we will be taking r cos theta for the velocity potential for the phi. So again I am writing for the phi, actually we are getting V infinite x, so this is actually equal to V infinite r cos theta. So this is very very important. Actually I am discussing those important topics that are actually frequently asked and can be asked in your ensuing gate examination. So as of now you can understand what are the topics and what are the formula you should follow for the uniform flow problems, or any kind of question if they ask from uniform flow. Now moving to the next topic, we'll be discussing about the source flow. As I've already said, with those stream function and then velocity potential, we are going to frame some new equation for source flow, sink flow, and also for doublet flow. So most of the cases they are asking about source flow and the doublet flow. So now we are actually concentrating on source flow. Source flow. So if I represent this source flow in a pictorial manner, we'll have something, one single source point, and from that the flow actually radially coming to the outward portion. So that kind of thing is actually the source flow concept. And you can have over here one equipotential line. This is the equipotential potential line, and these are actually the streamline. These are the streamline. So this is about the pictorial representation of this source flow. Now if I describe the mathematical representation, which is very much important for the source flow, I can have the gradient of the velocity vector is equal to 0, except the reason, because this thing actually will be there except the one singular point, that is the origin. In the origin this will not actually happen, but except the origin, all over the point this condition actually satisfies. And we'll actually take the radial component of velocity as and the tangential component obviously will be 0 for the source. Where we can have this, you can see the new symbol. Okay, so this kind of symbol actually is nothing but the source strength. Now if I illustrate what is source strength, the source strength is actually the rate of volume flow from source per unit depth. So this source strength is actually nothing but, the source strength is actually rate of volume flow from source per unit depth. This is the definition for the source strength. Now moving to the next thing. Now after knowing the definition of the source strength, we should consider the velocity potential for source, that is source strength by 2 pi natural log of r, and the stream function of this source flow is nothing but the source strength by 2 pi to theta. This is the two expression for the velocity potential and the stream function for source flow. And another condition, that is the circulation is 0. So the three things we have to consider for the source flow. And obviously another thing also achieved this source flow, that is the Laplace equation. We know very well, as I have discussed, is equal to 0, and then these two also satisfies in source flow condition. Now moving to the next kind of flow, which is very important, that is the doublet flow. So in doublet flow, we are actually in doublet flow we are actually having psi function, that is the stream function, and the velocity potential as well. and we are actually going to introduce some new term, that is K, that I will discuss for this doublet flow. So what will be the psi function or the stream function for this doublet flow? That is minus K by 2 pi sine theta by r, and the velocity potential is equal to K by 2 pi cos theta by r. Okay, so now when we get this new thing, that is the K, we should define what is K. We should know about it. So K is actually nothing but the product of the source strength and L. So what is L? L is actually distance between, L is distance between source and sink. So L is distance between source and sink. So this is about the K. So as of now you know the definition of the K, and therefore you know how the psi and the phi function, or the actually the stream function and the velocity potential for doublet flow actually derived. Now we should consider some typical case for gate point of view, as this kind of flow is repeatedly asked, and as they are very much potential problem, because they are judging your depth of aerodynamic knowledge. So those things actually I am going to discuss with you. First thing is non-lifting flow over a circular cylinder. So that is actually combination of uniform flow and the doublet flow. So uniform flow and the doublet flow. When we are combining these two kind of flow, we will be getting some non-lifting flow over a circular cylinder. So if I represent it in a graphical manner, I will be getting some tangential part. This is V theta, this is positive, and this angle is actually theta, and this distance is r. And if you represent in a pictorial manner, you will be getting something like this is a circular cylinder, and this is 2v infinite, here also 2v infinite, twice of v infinite both the side, and this is the v infinite, or the relative velocity. It is going to come into the cylinder, and the radius of the cylinder is capital R. Okay, so with this thing we can jump to the expression which is actually describing this kind of flow. So for non-lifting flow over a circular cylinder, we will be getting the stream function, that is psi is equal to v infinite r sine theta into 1 minus capital R square by small r square, where this capital R, as you know, the radius of this circular cylinder, and it is actually nothing but the under root of K divided by 2 pi v infinite, and this K, as you know, is the product of the source strength and the L, and L is the distance between the source and sink. Got my point? Now we can also derive the radial component of velocity for this flow and the tangential component. So what will be the radial component? It is the VR. VR is the radial component, and it is nothing but 1 minus capital R square by small r square v infinite cos theta, as it is the radial component. So we will be taking the cos part, and obviously for the tangential part v theta we will be taking minus of 1 plus capital R square by small r square v infinite sine theta, that is the perpendicular part. for the tangential part. Okay, so whenever we are taking the radial part, we should consider this cos part, and whenever we are taking the tangential part, we should consider the sine part, as it is the perpendicular part, and we know the tangential part is the must be the perpendicular part. Okay, now we should consider some case in this kind of flow. First case, when the small r is equal to the capital R and the theta is 0. This is one case. Another, when the small r is equal to the capital R and the theta is equal to pi. In both the case, we will get the stagnation point. In both the case, we will get the stagnation point. That means where the flow will be stopped. So this is the criteria to get the stagnation point. Basically, this value of theta you should remember. Okay. And further, when small r is equal to capital R and the stream function is 0, at that time also we are having a chance to get the stagnation point. Now, in another case, when the small r is equal to capital R and the radial part of this velocity is 0, that time we will be getting some tangential part, and that is nothing but minus of 2v infinite sine theta. Okay, so in this case we will be getting only the tangential part, no radial part. And the coefficient of pressure also we can derive from this case, which is denoted by Cp. That is nothing but 1 minus v by v infinite whole square, or we can arrange it, or we can simply write it by 1 minus 4 sine square theta. So this is also very important, and some conceptual question can be asked from this coefficient of pressure of this kind of non-lifting flow over a circular cylinder. Next, we should study about the vortex flow. So vortex, as we know, vortex is actually the wielding of some flow around this point. Okay, so in this case, the gradient of velocity vector will be 0 and the curl of velocity vector also 0. But there is some condition. The gradient of velocity vector 0 at every point. But the curl of the velocity vector will be 0, obviously at every point, except there is an exception, except the origin. So in origin, we will not get this thing as 0. The curl of the velocity vector will not be 0 at the origin. Okay. So this is about the vortex flow, and now you know the vortex flow. In case of vortex flow, the radial component will be 0 and the tangential component will be minus of tau by 2 pi r. Now what is this tau? This tau is the new term which has been introduced, and this tau is the strength of this vortex. So tau is the strength of this vortex, and here are some convention, sign convention for this tau. That means if my tau is positive, if my tau is actually positive, that means clockwise vortex, clockwise direction, the vortex is taking place in clockwise direction. And if it is negative, that means it is taking place in counterclockwise direction. Okay, so this sign convention you should consider if you actually doing some problem regarding this vortex flow. And other thing that you should remember about this vortex, that is the velocity potential of this vortex flow, that is phi, that is equal to minus tau by 2 pi theta, and the stream function, that is psi, is equal to tau by 2 pi natural log of small r by capital R. So this is very, very important. Actually, I am discussing the important topic. So actually, I am discussing about this basic fundamental things, and the more important topics from this aerodynamics, as whenever you are just revising those topics, once you go through the topics from the book, and I especially recommend Anderson book, because there it is clearly described and very descriptively it is actually well explained there. You can understand the concept behind each individual expression, and when you have understand all those expressions, you can straight away answer all the questions, because in GATE and this kind of competitive exam, they are actually judging the ability of your comprehension about the subject. So whatever your understanding, they are actually judging. So once your understanding is very clear, crystal clear, then you can go through any kind of question. So do not just solve the previous year's question blindly by mugging up all the options and all this thing, but just remember the topic and go through the topic. Whenever you are just solving something in previous year's question, do not just solve the simply that simple question whatever they have asked, but you just choose the topic from where the question is actually picked up and study the topic from the book. This is my suggestion for you. Now when we discuss about this vortex flow, we should discuss the lifting flow over a cylinder. Actually, we have discussed non-lifting flow over a cylinder. So we should discuss about the lifting flow over a cylinder, where we are getting combination of three flows. One is uniform flow, another is doublet flow, and obviously another is vortex flow. So punching this three flow, we will be getting lifting flow over a cylinder. Okay. So this kind of fact you should memorize, so that you can proceed any kind of logical type question they ask in GATE. So what will be the psi function, that is the the stream function for the lifting flow over cylinder, that is psi is equal to V infinite R sine theta 1 minus capital R square by small r square plus tau by 2 pi natural log of small r by capital R. This is the psi function or the stream function for lifting flow over a cylinder. Okay, because we are combining all these three flow and we will be getting this kind of expression. Now we can get the radial and the tangential component of the flow for this kind of flow over a cylinder, lifting flow over a cylinder, that is VR, that is the radial component is 1 minus capital R square by small r square V infinite cos theta. As I actually mentioned earlier, if I take the radial part, you should take the cos theta, this cos part, and for the tangential part it will be minus of 1 plus capital R square by small r square into V infinite, obviously sin theta part, because the perpendicular part you should take for this tangential consideration, minus tau by 2 pi r. So this is the two part, very important for the lifting flow over a cylinder, circular cylinder. Okay, because if you understand this lifting flow over a cylinder, suddenly you can understand what is Kata-Jakowski theorem. I am just proceeding towards that theorem only, but before that I am just make you understand about this basic fundamental aspects of the theorem. So with this knowledge we can proceed further to find the stagnation point. So for stagnation point when actually the flow is actually there is no flow. Okay, so there the small r is equal to the capital R and theta, and the theta, this is the very much important thing, theta is equal to sine inverse of minus tau by 4 pi v infinity r. So this theta, this angle is actually coincide on third and fourth quadrant. That is why we are getting this kind of value. Okay. Now, after getting the stagnation point, this we remember this theta is equal to sine inverse of minus tau by 4 pi v infinite r. So we take this tau by 4 pi v infinite r, this portion. So if this tau by 4 pi v infinite r is if it is 1, if it is equal to 1, definitely one stagnation point will be at theta is equal to minus by 2, and if this part, that means if this tau by 4 pi v infinite r is less than 1, then there are two stagnation point on the cylinder. You should remember, if this is less than 1, there will be 2 point stagnation point on the cylinder, and another case, if this is greater than 1, that means tau by 4 pi v infinite r is greater than 1. If it is greater than 1, then obviously two stagnation point, one is inside and another is outside the cylinder. Should get two stagnation point, but one is inside and another is outside the cylinder. When we get this tau by 4 pi v infinite r is greater than 1 and this two stagnation point, one is inside the cylinder and another is outside the cylinder, obviously we would be getting the lift, that is L is equal to rho infinite v infinite tau. So this is a very important relation, and from this relation we'll be having, this is actually lift per unit span. Okay, and from this relation we'll be having lift is actually proportional to the tau. And my dear student, this is nothing but your Kata-Jakowski theorem. This is the Kata-Jakowski theorem. Okay. So this is all about this Kata-Jakowski theorem. Now moving to the next part, that is the characteristics of aerofoil as a NACA nomenclature. As I have already discussed about the trailing edge, chord line and the thickness, mean camber line, chord, all of these things earlier. So directly I am going to the nomenclature of aerofoil. So I will give some example And through those examples, I will make you understand about the aerofoil nomenclature, like NACA 2412. This kind of nomenclature is there. We will abbreviate this thing and we will actually expand this thing as the maximum camber of this aerofoil. The max camber is 0.02 of chord. So 0.02 of chord, at that point you are getting the maximum camber, and at 0.4 of chord from the leading edge, you are getting the maximum camber, and the maximum thickness you will be getting, in this case maximum thickness you will be getting at 0.02 of chord. So how it is actually happening? Let me give another example and let me show you just separately individual part of this thing. Let me take another example. So NACA, so this is actually NACA is actually giving the aerofoil nomenclature. This is the advisory country for design. Designated names are actually given by this authority, and they are actually the apex body for the nomenclature of the aerofoil. So if NACA 23012, if this is the nomenclature, so we can separate this thing as, we can have this 2 into 3 by 2, that means 3. So at 0.3 is the designed lift coefficient. Okay. So this is the first part. So lift coefficient we can understand from this, and here we are getting this 30. So this 30, if we just divided it by 2, you can see if we divided this 30 by 2, we will be getting 15. So 0.15 of chord. This is the location for maximum camber. This is the location for maximum camber. 0.15 of chord is the location for the maximum camber for this aerofoil. And you can have this 1, 2 over here. So 0.12 of chord denotes the maximum thickness. So at 0.12 of chord you will get the maximum thickness for this kind of aerofoil. So getting my point. Let us take another example. NACA 65-218. So this is actually 6 is series designation. So you can have this 6. This is the series designation. So this particularly this 6 is the series designation, and the minimum pressure is at, you can have 5 over here. So minimum pressure is at 0.05 of chord. You can have 0.05 of chord. At that place you are having minimum pressure for basic symmetric thickness distribution. and you can have this 2 over here. So 0.2 is the lift coefficient. This 0.2 is the lift coefficient, and last you are having 1.8, so 0.18 of chord is that position where you are getting maximum thickness. So getting my point. So first 6 is the actually it denotes the series, the aerofoil series. The minimum pressure is about 0.05 this of chord. So this is a 5, and this 2, this 2 is actually denoting 0.2, that is a lift coefficient, designed lift coefficient, and this lastly this 1 in, that means 0.18 of chord actually denotes the maximum thickness of this aerofoil. So this is all about the nomenclature, NACA aerofoil nomenclature, which is also little bit important because maybe one question can be asked from this nomenclature, and you can go through Anderson books again to get a detail about this nomenclature and to work out more examples. Okay, so that you will be very familiar with the nomenclature, and you can very easily actually expand, or you can very easily identify what kind of aerofoil is this. Okay, so again I am coming to the lift coefficient and angle of attack, this curve, because this is very important curve. And one thing, my dear student, you should remember that infinite wing is actually almost equal to the aerofoil. Actually, for infinite wing we should consider it as aerofoil. So when we are considering this CL versus this alpha, that is lift coefficient and this angle of attack drag, so this curve, so here at that point, though the angle of attack is actually 0, but you are getting some amount of lift coefficient due to the camber of the aerofoil. Okay, so that is for the cambered aerofoil, not for the symmetric aerofoil. And this A0, as you can see over here, this is a slope, that is the dCl by d alpha. This is the slope over here, and this A0 is actually not influenced by the Reynolds number. Reynolds number is nothing but it is denoted by actually Re, and is actually ratio between the inertial force and viscous force. Inertial force and viscous force. So this A0, this slope is not actually influenced by this Reynolds number, but the CL max, this lift coefficient max, depends on the Reynolds number, because CL max depends upon the viscous effect. As it is actually Reynolds number is the ratio between the inertial force and the viscous force, definitely maximum lift coefficient depends upon the Reynolds number. Okay, so these are the points you should remember, because they can ask some logical question, okay, from this, some dependency of lift coefficient with the Reynolds number or with the slope of the lift coefficient and the angle of attack. This kind of question they can ask. Okay, and if for an aerofoil, if the drag d dash, that is the profile drag, is actually the summation of screen friction drag and the pressure drag. So this is also very important point you should remember, because when we are discussing about drag, we know the profile drag or the total drag of an aerofoil is actually the summation of the skin friction drag, the drag due to the skin friction, the friction between the relative wind and the skin of that wing or any kind of aerofoil or any aircraft. So that is the skin friction drag, and P is the pressure drag. Okay, and this pressure drag also known as form drag. You can name it as form drag also, form drag. Okay, because this drag is actually happens due to the flow separation. Okay, this profile drag or this this d dash is actually depends upon RE. It depends upon Reynolds number. It depends upon Reynolds number. Okay, and this screen friction and this form drag or the pressure drags both are effect of viscous force. Okay, that is why the profile drag is actually depending on Reynolds number. So this kind of dependency they can ask in any question. Okay, and the aerodynamic center. Okay, they can ask some concept about aerodynamic center. Aerodynamic center can be represented by this AC, so aerodynamic center. It is actually the point where the moment is independent of angle of attack. The moment of that aircraft is independent of angle of attack. At that point is known as this AC or aerodynamic center. Okay, now if we move to the next section, that is very important, that is the Katta condition. That is the now moving to the very important topic, that is Katta condition. That is very much important topic to discuss in aerodynamics point of view, and especially in GATE they can ask this kind of fundamental question where they can judge your comprehensiveness about this subject. So moving to the topic of this Katta condition, where we can have at a given angle of attack, that is alpha, the value of tau, that is the vorticity or that strength of that vortex, is such that the flow leaves the trailing edge very smoothly. So actually of trailing edge the angle is finite, and if the trailing is the stagnation point, that means if this is the stagnation point where can reach the stagnation point over here, so this is the velocity from the above of the aerofoil, that is denoted by v1, and this is the velocity below of the aerofoil, which is actually v2, and this both thing will be 0 because of the stagnation. Because of the stagnation, this both thing will be 0. So this is one case. So basically we'll be having over here the is equal to v1 minus v2, and that is equal to 0. And for definite case, for in case of cast trailing edge, so for cast trailing edge, that is fully aerodynamic shape, this is cast trailing edge. So there the flow from the both the side actually will continue, and this will be equal to each other. So velocity will be equal to each other, but that is not is equal to 0. So that is very much good condition. This is ideal condition for getting maximum amount of streamlining flow and very smooth flow. And if this kind of flow which is adhered to that aerofoil till it is, when it is leaving the trailing edge of the aerofoil till it is parallel to each other, so it will establish maximum amount of lift, and it is actually avoiding the flow separation condition. Therefore it will have a maximum amount of performance. So this is what about the Katta condition is. For incompressible flow from Bernoulli equation we should have some equations like incompressible flow for Bernoulli equation, P plus half of rho v square is equal to constant, and the energy equation for the incompressible flow is H plus v square by 2 is equal to constant. And other thing that we should remember, that is the Mach number. Mach number is nothing but velocity of object to the velocity of sound, and this A is actually under root of gamma t. Okay. And for isentropic relation, those things we should remember. For isentropic relation, P by P1 is equal to rho by rho 1 to the power gamma is equal to T by T1 to the power gamma by gamma minus 1. So those are the isentropic relation we should consider in case of incompressible flow from Bernoulli equation. And from this equation we can have some some other expressions. Those are like Tt by T infinite is equal to 1 plus gamma minus 1 by 2 m infinite square, and similarly rho T by rho infinite is equal to 1 plus gamma minus 1 by 2 m infinite square to the power, here you are having something to the power 1 by gamma minus 1. So these are some complex relation because those are isentropic relation, and definitely likewise you will be getting one pressure relation also, that is Pt by P infinite is equal to 1 plus gamma minus 1 by 2 m infinite square to the power gamma by gamma minus 1. So actually why I am saying all this equation, because these equations are very important, and not only for aerodynamics, if you are just doing some problem in gas dynamics or in propulsion also, these are very useful problem that you can actually make of use of this kind of problem. So this is all about the incompressible flow from Bernoulli equation. Now for compressible flow, if we use the Bernoulli equation for compressible flow, we'll be having like gamma by gamma minus 1 into P1 by rho 1 plus V1 square by 2 is equal to gamma by gamma minus 1 into P0 by rho 0 is equal to gamma by gamma minus 1 P2 by rho 2 plus V2 square by 2. So this is for compressible flow Bernoulli equation. Okay, and from this Vmax we can derive for compressible flow. Vmax is equal to under root of gamma by gamma minus 1. Okay, and so this is Vmax for compressible flow. At the same time, this Vmax for compressible flow is actually under root of gamma by gamma minus 1 times of Vmax of incompressible flow. Again I am repeating, V max of compressible flow is equal to under root of gamma by gamma minus 1 times of V max of incompressible flow. Now what is actually then V max of compressible flow? V max of compressible flow is actually V max of compressible flow is actually under root of 2 gamma divided by gamma minus 1 P0 by rho 0. What is the V max for incompressible flow? So V max for incompressible flow is equal to under root of 2 P0 by rho 0. And what I have discussed earlier, that is the relation between these what is relation between V max of compressible flow and the incompressible flow. That is nothing but V max of compressible flow is equal to under root of gamma by gamma minus 1 times of V max of incompressible flow. Okay, so this is actually the important topic what we should consider for our aerodynamic point of view for GATE 2021, and other things related to aerodynamics that you can have in your propulsion section also, but these are the hardcore aerodynamics section or the portion whichever I have discussed here. Just go through this thing, try to solve some problem using this kind of formula whichever I have here discussed. And I just request all of you just to go through the previous year question and not only just concentrate on the question, but just see from where the question is actually taken from. Just read that portion from the textbook, especially from the Anderson book, and read the related topic from that question. Not only that question, some other question can be asked, so read full topic and then just go through my lecture and try to relate this lecture with the book and then solve the question. By that way you can easily go through all the question and you can easily solve the questions. And if any difficulty you just have in solving all these things, you can just get back to me by Team 2020, and we will be having one doubt clearing session definitely maybe 1 month later before your GATE exam, and we'll be discussing some problem from the GATE question years, previous year's question. But my suggestion again, don't only go through the question, go through the textbook very clearly, because from the GATE they are not going to repeat any kind of question, but they are just there asking you some question to judge your knowledge, to judge your basic concept. So just mugging up all these topics and all these things is not going to help you to go through the GATE. So if you want to clear GATE, you should have very clear knowledge about each individual topic. So just more you just read those books, your knowledge will be clear. Okay, so all the best for your GATE exam. Hope you will meet soon to discuss some problem related to GATE. Stay safe, stay healthy. Okay, take care.